Okay, I hope you can see it. So the outline of today's talk will be like a short introduction about this Tennant's law. Then we would separate the two limitations. First, we go into the speed limitations, and then later on the resolution limitations for the NanoFrazor. And we see in like a short outlook how we can also combine our technology with other combinations of like mix and match or other ideas how to combine and get more speed and throughput. So just to start with, that we are all on the same page. This is basically what I guess you're kind of familiar. That's the principle how the NanoFrazor is working. So you start with a certain grayscale kind of input file, where then the grayscale is converted into an electrostatic force between the tip and the substrate, which then results in a certain depth U pattern. And this we do in the forward direction with a hot tip. You can see how the tip is basically hot. And then we go into contact modes. We turn off the tip, so the tip is cold, and we just read back our image. With that, we get like a direct in situ information of our topography written. So that is how the NanoFrazor works. So let's go first into the first introduction. So this Tennant's law is like an empirical law, like Moore's law, and it basically states that the throughput goes with the resolution to the power of 5. And if you check here in this graph where you can see the resolution versus the throughput, you can see if you compare even with e-beam lithography, like well-established technology, you can see that even that technology is spreading over the range of like 10 orders of magnitude. So depending on the process and the e-beam used, you even can have a different like range of that regime, patterning regime. So the same is also kind of true with the scanning probe lithography, which is like our technology. You can see that also the scanning probe lithography is over the range of basically 10 orders of magnitude. And if we check that we are not needed this high vacuum, we are just in the ambient range and more on the higher throughput side. So if we zoom in into this zoom in here, we can see that also resolution versus throughput, we have different technologies for scanning probe lithography. But the cool thing about our thermal scanning probe lithography is the fact that we are like a lot faster, and this is due to our kind of reaction, how we do the decomposition. And what is also to say here is basically you might have to think also that it's not enough to get the resolution and the throughput, but you also need to have it a certain depth. So in this case here, where you might have only like an angstrom of indentation, that's maybe for resolution a proof, but you cannot really transfer such a structure into the material or you desire. So that's also to keep in mind that this is not the whole truth here. So then we go into like the speed limitations, which is the first part of the talk. So the first limitation is basically the question also how long the tip needs to stay. So what is the reaction time limiting? And if you compare it to other SPL techniques, like anodic oxidation or dip and field emission, just for some examples, you can see the whole reaction always needs a certain time to get induced and triggered. And this is in the range of milliseconds. When we compare it to our thermal SPL patterning, we are basically the heat transport itself happens already in the nanoseconds, but we need a certain like contact time to trigger our decomposition of our resist. But we are not in the milliseconds, we are like a factor of 1,000 faster with these microseconds of time. So there's one thing if you plan to also do like conversion of the material, so you induce some change in the material rather than the decomposition of our special PPA resist, then it might also need a little bit of longer heating times. So comparing to other SPL techniques, we are way faster. So after the reaction is not a limiting thing. The question is how fast we can kind of on and off switch our cantilever. And you can see how basically the resonance frequency itself for our cantilever is in the range of 150 kilohertz, and that's basically the speed we can kind of turn it on and off at and run it at the resonance frequency. So if the cool thing is that we even can pattern above the resonance frequency. So you can see once we kind of try to get the cantilever in contact and we actuate, you can see how actually the cantilever oscillates into its static position. But if we actuate even with faster pulses and strong faster pulses, we can even operate at above this frequency. So which is here like 500 kilohertz. And in this case, we just patterned this field with like 2 microseconds between these 2 pixels at 40 nanometer pitch. And this was kind of like a very high speed result. And we published this in 2011. So the question is, when you're using it at such a high speed, the challenge is how good is the positioning accuracy and what are the out of plane movements. And so with this high speed, we're basically at this 20 millimeters per second, but that's very challenging. So our solutions are like two-folded. One is we are doing with the hardware. So we have very advanced piezo stages. We collaborate with the suppliers to get very stiff stages with high resonance frequencies. And we have like very advanced design solutions and sensors. The other part from the hardware is the software and also like the control schemes we are using. So we have special like of actuation of the turnaround. We optimize the turnaround, and we also use feed-forward corrections and like a model-based trajectory to optimize the whole trajectory during operation to minimize the out-of-plane movements and optimize the positioning accuracy. So, and that's very interesting. So still, like you saw how we can operate at this 20 millimeters per second in this publication, but as you might all be aware of, there's not always all the truth in these papers. I want to share today with you what is still the problem here. So if you're operating at this over the resonance frequency, you are very sensitive to the actual pulse durations. And this you can see here, basically, if you compare to the left to the right, how sensitive it is just for minor changes in the pulse duration. So either the tip then sits too long at a certain time and it just removes too much material, or it doesn't pattern too deep enough. And so what's to kind of like, what is then more not the ideal solution, but more a practical case. And the real case is basically that we operate at these 30 microseconds of pixel times, which then are basically at scan speeds of 1 millimeter per second, which then translates to the like roughly 1000 micrometers squared per minute of aerial throughput. So the only thing here is to add is that you also keep in mind that you don't not only do the patterning in one go, but you also get like directly an in situ information of the topography. So this is also kind of considered here. So if we compare also this patterning technique to the speed to other like beam technology like FIB or EBL, you can see that basically we are limited due to the beam current we need to induce the change in this high sensitive resist materials. We need a certain dose and what is kind of a practical range to operate this beam technologies is basically you're below the 1 millimeter per second scan speeds. And that's also the fundamental reason why even for like advanced EBL systems, there is some parallelization. For example, just to get you aware, like this is basically like a very high advanced parallel E-beam machine. And here there's like incredible 260,000 of E-beams used in parallel to get this 40 nanometer resolution in a high throughput. So, but then after the patterning, this is also not the whole story. And there's more than this writing speed. If you compare it also, you need to have for your lithography tool, like a certain sample preparation to be made. You have some data preparation which needs to be fed into the system. You need the machine setup itself. You need to align your structures, which always takes a lot of time. And also then the processing and the inspection afterwards. So if you all compare this together, then in certain cases, the throughput or the overall turnover of using the NanoFrazor could be a lot higher than with e-beam or other beam technologies. Just because we are kind of in this cycle of where we can just pattern and see already the inspection during the patterning. So we don't need to make a lot of dose tests or run a lot of patterns just to find the one structure which then worked. We can just see immediately which is the most promising pattern we want to kind of continue with the processing later. So the message here is that also the overall turnover for speed needs to be considered, and we are very compatible with the NanoFrazor here. So after going into the speed limitations, now we go into the resolution limitation. And the first thing I want to share with you, there is still like a difference if we talk about like simple features or one critical dimension, like here where we just shrink the gap here. This we can just program easily with the NanoFrazor. But the question is more like, what if we have more dense, complex shapes where there is a different density of pixels to be written on a certain line? This is like more advanced, and the overall accuracy and fidelity of the pattern is more demanding. I'm pretty sure we are all aware that the most obvious reason why the resolution is limited is the tip itself. So we normally have like a tip apex resolution or tip apex radius of around like 5 nanometer. You can see here in this TEM image our tips. And what you don't want is basically that you pattern too deep into the resist. Because of the cone shape, you will also, the deeper you pattern, the more line width you will create. That's basically also what you can see in this sketch. So if we pattern deeper, we will also increase our line width, and that's basically also limiting our resolutions. So the result of that is that we actually would like to not only indent very shallow into the pattern. I will come back to this later in the talk. So after the resolution from the tip, there's the other part of the system, and that's basically our resists. And you can see here just that we have a lot of variety of resists you can use. You can use like polymer systems, or you could also use these molecular glasses, but there are always like some issues to be considered. Either it is like a low mechanical stability, so you have just what we call this pile-up present, so where you just like plastically deform the material and you just see then this pile-up happening, or you have like very sensitive materials, so it's difficult to operate at the correct temperature applied because the line width is very depending on the temperature. Or you have like thermal flow, and you can see how you then squeeze around your material. So there are several issues with different polymer systems. And the idea of the molecular glasses was basically that you have like a smaller molecule, so you would have like less limitations from the resolution. But the problem is here with these small like molecules, or this idea of molecular glasses, that they are not stable in time. So you can see after like patterning at the first read, we see how the structure was kind of looks, but then after just a second read, some minutes later, we then see how the pattern got more shallow and also gets smeared out. So, and this is also due to the surface diffusion of these small molecules, and that's not optimal what we want. And finally, that's also the most important thing for the tip endurance of your NanoFrazor operation, is basically how much residue we then pick up at the tip. So ideally we want to have a material which just like directly sublimates and decomposes completely without any residue formation. And that brings me to the actual system we are using at the moment as a gold standard. And we collaborated and commercialized this resist together with our supplier Allresist. And the cool thing about this polyphthalaldehyde, or PPA, how we call it, is that it basically just comes from its polymer state in the solid state. And once you induce the heat trigger, it just directly decomposes into its all monomer. And this in a non-zipping fashion. So, which means once you break a certain bond here, like all the molecules one after the other just unzip by itself. So it's an amplified reaction. And that's very cool. So also because this decomposition process is endothermic, which means it consumes the heat itself. So, which then means that it's basically very self-limiting in size. So that's basically ideally what we want to have for a resist. And you can see how much, like in the examples, what we could do with this high-end polymer system, which is available to buy from Allresist. Just want briefly to mention, if you want to know more about the resist materials and tip lifetime, my colleague Jonas will have a talk next Wednesday about this. And just to convince you also that this is not something you just do like on a small range. You can even do this high resolution of, in this case, this 27.5 nanometer half pitch structures, and you pattern this over like tens of microns of area. So there's like a high stability on the process. So after the tip and the resist, we still have like a parameter space of temperature and force. And you can see here when we kind of make this map between varying the temperature and the forces for our operation, we see that we have basically three regimes. So if we are too high with the temperatures, basically somewhere here, you can see if you make a cross section that basically you have like neighboring pixels which just got like decomposed because of the heat flux is too big between these neighboring pixels. So you also get this kind of recess here where it's basically the resolution is lost and your final amplitude you can transfer is then shrinked. The other thing is if you're like too low with temperatures, then you have more this kind of plastic regime where you're not fully in that kind of speed range we are operating, decompose the polymer enough so that we still have this kind of pileups next to the lines. And this we also don't want, because ideally we want to transfer like the zero level. So there is a certain optimization in this parameter space between temperature and force to get like the highest amplitude possible, which then enables an easy RAE transfer process. Which brings me to the next point with the pattern transfer. And if you remember that I told you also because of the resolution, we want of the cone shape of the tip, we only want to pattern like in very shallow resists in this case. So we established over the years a process with like this kind of silicon oxide based hard mask, which you even can use a spin on glass, so it's spin coatable, and then transfer your structures into the hard mask or any required materials afterwards. So, and also over the years, you can see how we could shrink the structures from the set 27 to basically roughly the 10 nanometer half pitch range. And just a small word about the line edge roughness. Also here we are pretty compatible with like line edge roughness of around like 2.3 nanometers in 3 sigma. So just like this is not only pattern data, this is really transferred structures. And also if you want to know here, there is my colleague Emine having a talk on the 4th of June about all these high resolution etching processes. So after the two limitations, I would also like to give you an outlook of what are still options to combine our technology. And the first one we developed together with Heidelberg, our mother company, is this laser mix and match. And the idea here would be like that you basically can still use the same tool and the same resist layer to combine the tip and the laser operation. And the idea here is that basically with the laser, you can just have like maybe a micrometer size spot, and with all the structures in example like here, where you just see this design, you don't need everywhere the highest resolution, right? So, and because also the tip is consumed, you might want to have high throughput, no contamination using the laser for the bigger structures, and then only kind of do it in the smaller like areas where you have special requirements for resolution, use the tip. And so with that, you can even, for the overall design of your pattern, you can even increase like by a factor of 100 for these micro features with the laser writing. And so how this is done in this example here, where we installed the first system at Harvard CNS last year, was basically this was done first with the laser, which in this case we decided to use a 405 nanometer CV laser, and did afterwards the tip pattern next to it. And then finally we made a whole inspection of the whole patterning with our in situ kind of read only operation mode. And so you will get also even the inspection, and you can align the laser and the TSPL together. So that's the one idea about the laser mix and match, but still maybe you want to still have the resolution, but to increase the throughput there, we are going into the direction of multi-tip. So basically at the moment we are like finalizing the fabrication of this multi-tips, where you can see this is an array of 10 tips. And we even try to commercialize this by the end of the year, where you can use 10 cantilevers in parallel to get like higher throughput. And just to give you a hint of where we would like to go with that idea is basically in the late 90s, or with the IBM Millipede project, they already proved that they can operate these 4,000 cantilevers in parallel. So there is a lot of room to improve also for our technology in this regards, and that's we are very much pushing. And the last idea is also that we, even if you care about the scaling up of your designs, then basically also you can focus on the master fabrication, even use our 3D operation with our technology, but then just like use well-known nano imprint to then just like fabricate bigger devices. And also here, my colleague Tero will have a talk about especially these techniques of nano imprint and injection molding combined with our technologies. So just to briefly summarize, for the speed, we are like very fast with our reaction of this decomposition of the PPA in the microseconds regime. We optimize our actuation of the stages, and we are then roughly operating at this 1,000 micrometer squared per minute. You should always care about the full process, so the full turnover of your whole pattern transfer, not only the patterning itself. And then if you consider also the laser writer combination, the multi-tip or the nano imprint, you can even increase your throughput beyond the NanoFrazor speed itself. And the other part of the resolution, basically we are already like at 10 nanometer half pitches, and we really also try to push for lower critical dimensions here. And there's also a lot of like a well-established pattern transfers from our side, so we could also help you a lot and support for any materials you would like to transfer. Yes, so with that, I might go back to Felix and we go into the question and answer section.